We're going to talk about molecular shape some more, but also bring polarity into this. So if we have a diatomic molecule, just two atoms, simple molecule, get the pointer going, there it is, like HCl. We learned about electronegativity, and we learned that fluorine is the most electronegative element, and so you can pretty much just predict by position on the periodic table which is going to be more electronegative. So we see that chlorine is closer to fluorine in the periodic table, and so we predict that it is more electronegative. This means that this is a polar covalent bond. Those electrons are not shared equally because chlorine is more attractive. Just like in the little boy analogy, chlorine's house has a lot more fun stuff. And so the electrons, the two little boys playing, are going to spend more time over there. So this gives us a lopsided electron distribution. So we've got the electrons spending more time over here. This end of the molecule is negative just a little bit, and this end is just a little bit positive. So that's a polar bond. That makes this molecule polar. When we have more than two atoms, things get a little more complicated. So then the polarity of the molecule is going to depend on the geometry of the molecule, and that's why we had to look at geometries first. For diatomic molecules, the molecule is polar if the bond is polar, but polyatomics, we have to look at the geometry. Dipole moments actually are vectors. Vectors have a magnitude and a direction, and you can add vectors together. Vectors can add up to 0, or they can add up to something other than 0. Sometimes in a polyatomic molecule, you have all polar bonds, but because they are all aligned in a very symmetrical way, there's no net dipole in the molecule, and the molecule itself is nonpolar. So let's look at carbon dioxide. This is one of the easier examples to understand. So here we've got an illustration, a model of carbon dioxide. Carbon dioxide is a linear molecule because there are no lone pairs on the carbon. There's just the two electron groups, and so they get on opposite sides of each other, and we have a linear molecule. So the carbon-oxygen bonds are polar. And again, I'd like you to predict any two different elements. I'd like you to predict that that's a polar bond except for a carbon-hydrogen bond. Carbon-hydrogen bonds are just on the edge between polar and nonpolar, and so we consider them to be nonpolar. So let me write that down because it's not official unless it's written down somewhere, right? Carbon-hydrogen bonds are nonpolar. And the reason I want you to remember that one is because carbon-hydrogen bonds are very common in organic compounds, and so we see them a lot. The others that are nonpolar aren't worth remembering, in my opinion, at least not at this point. So these bonds are polar. Oxygen's more electronegative than carbon, and so in this bond, oxygen is pulling the electrons away from carbon. And in this other bond, the other oxygen is pulling the electron density away from carbon. So you could think of this like two people playing tug of war, right? So here's one person, and here's another person. I don't usually get this elaborate, but here we've got the rope. Well, you get the idea. And no, that's not a good color, and I already used red. So, we got this. That didn't work. So we got a little flag on the middle of the rope, right? It's two guys pulling, and you got to get the flag across a line, and then you win the tug-of-war contest, right? So imagine these dipole moments as being people pulling on a rope. They are pulling in the opposite direction of each other, and they are equally strong. If you have two equally strong people pulling on this rope, is that flag going to move? No. You're just at a standstill. They're working as hard as they can, but nothing's going anywhere. This is a nonpolar molecule, even though the bonds are polar. because they cancel each other out. They're opposing each other. So if we look at electron density for this molecule, there's a little bit less electron density in the center than there is on each end, but we don't have one end being more negative than the other. Does that make sense? If we think about adding vectors, in math they represent those as arrows. So you've got the direction, and then you've got the length. The length is the magnitude, so in this analogy, how strong the person is, and the direction is the direction that they're pulling. So if you've got two arrows going in opposite directions of equal length, then they cancel each other out and they add up to 0. You guys at least have a vague memory that sometime you learned about vectors? Yeah? It's one of those things that you don't actually use too much, but if you graduated from high school, you should have heard about vectors. So let's look at water. Now, if you look at if you just draw a Lewis structure for water, let's get away from the red for a minute. You've got H, O, H, and yeah, we've got those two lone pairs, but whatever, right? So if you just look at that, you'd say, oh, well, that's linear, right? The hydrogens are on opposite sides of the oxygen. But that's not what's going on, right? We learned that you have to look at the number of electron groups on the central atom. This has 4 groups, 2 lone pairs, and 2 bonds. You think about what do 4 balloons do? They make a tetrahedron. So those 4 groups make a tetrahedral shape. To find the molecular shape, you think about, well, what if those lone pair balloons were invisible? What do I have left? And we've got something like this. We have a bent structure. It's actually really important that water is bent and not linear because it drastically affects its properties. So this is the structure. These are also polar bonds. They are equal in strength because they're between the same 2 elements, hydrogen and oxygen. But now oxygen is pulling density from hydrogen at an angle, and it's pulling density from the other hydrogen also at an angle. And so in the tug-of-war analogy, let's see if I can do this. Oops, that's not exactly what I wanted to do. So here we have, maybe this is Dad, right? And then these are his twin sons, little guys down here. And he's got a rope, and each of the boys has a rope, and Dad's pulling, right? Is Dad going to move the rope? Sure he is. He's stronger, right? And even though the boys are pulling at an angle from him, he's going to move the whole business backwards. Can you imagine that? If the boys were on his right and his left pulling opposite, even though Dad's stronger, they're not going to go anywhere, right? Because if he pulls to one, then the other one gets an advantage. But here at an angle, we have an overall movement of the rope. In terms of vectors, we have a vector going this way, and we have a vector going that way. Those are going to add together. And the overall vector is smaller in magnitude, but it has a direction and it's not 0. So water has an overall dipole moment. It's a polar molecule. The oxygen end of the molecule is slightly negative, and the hydrogen ends are slightly positive. Any questions yet?
What properties would water have if it were linear?
Well, if water was linear, it would be nonpolar, and that would affect how attracted the individual water molecules are together. And so just like carbon dioxide is a gas at room temperature, water would be a gas at room temperature. And that would drastically change, well, it wouldn't even be life as we know it. There wouldn't be any life if water was a gas at room temperature, because all the water in your body would vaporize. Ooh, yeah, right? Not that it would be hot, but it would just all turn into gas. So that just wouldn't work. And all the oceans would turn into gas. And yeah, that'd be weird, huh? That'd be really weird. And we're going to learn, probably more than you want to, about exactly how the polarity of water affects its properties. Anybody else have any questions, comments? Let's make sure I didn't skip anything. There we go. Okay, so this is a summary slide here. To determine the shape of the molecule and the polarity of the molecule, you have to start with a Lewis structure. From the Lewis structure, we determine the molecular geometry. Those are the first, that's the previous chapter and the earlier part of this chapter, right? Like summarize all of that in one, not even a sentence. Next, you decide, does the molecule have polar bonds? And if it does, you indicate those polar bonds with vectors pointing towards the more electronegative atom. The length would be proportional to the change in electronegativity. So this is a more detailed description. In practice, though, we generally just have to look at the direction of the vector. We don't actually generally have to consider the length at the Chem 1A level. So that makes it a little bit easier. Then you have to decide if the polar bonds add together to form a net dipole moment. If the vectors sum to 0, the molecule is nonpolar. If there is a net vector, then the molecule is polar. So I'm going to explain a little more about the adding vectors, but then I'm going to give you a shortcut that you can do. You can get most of these correct without understanding what vectors are. So let's just review vector addition. Right? In one dimension, it's relatively simple to think about. So here in example 1, we have two vectors. They each have a magnitude of +5. They're going in the same direction. That adds and gives you a vector in that direction that's +10. This is a little bit like a number line, okay? You remember those, right? So here we've got a line with numbers, and there's 0 and 1 and 2, and here's -1 and -2. Oh, that's weird delay. So 5 to the right and 5 to the right would be just moving 5 spaces to the right on the number line. And that would get you 10 spaces to the right from where you started. Yeah? If we have vectors going in opposite directions, so this one's going 5 to the left, negative, and this one's going 10 to the right, positive. So that's adding a positive and a negative number, and that'll give us +5. So starting here at 0, going -5, and then +10, we get a +5. This would be like people playing tug of war, pulling in opposite directions, but this guy is twice as strong as that guy. And so overall, things are going to move to the right. And then in this example, example 3, we have vectors that have equal magnitude, but they're in opposite directions. So one's -5, one's +5. That adds up to 0. Any questions? What if you have more than one dimension? Well, things get a little more difficult. So let's think first about 2 dimensions. So here we're going to add this vector A and this vector B. And we can do this graphically. So draw them out with their angles. And then what you're going to do is you're going to take and draw from the end of vector A, you're going to draw a line that's parallel to the other vector. And from the end of B, you're going to draw a line that's parallel to vector A. The sum of those 2 vectors is where those 2 lines intersect. Well, let me just do another one. So let's say we had one going like this, and we had one going like that, and we're trying to see what would that give us? How would that add together? So from the end of this vector, I'm going to draw a line. I'll try to make it dotted. That's parallel with the other vector. And then I'm going to draw a line over here. Oops, that's not. So we're making a parallelogram. You're saying, well, these vectors are two sides of a parallelogram. A parallelogram, the sides are parallel, but the angles could be just about anything. So then adding those together is going from this origin point to where those parallel lines meet. Any questions? We're not going to get into angles and signs and adding and deciding are the magnitudes exactly the same or anything. We're going for big idea here, not details. What if you have three vectors? This is where you could have 3 dimensions. Well, you can't do 3 dimensions all at one time. If you have 2 vectors, because they are lines, you automatically have 2 dimensions, not 3. But if you have 3 lines, you could have 3 dimensions. So add 2 of them first, and then add the third to the result of the first 2. So here we've got A, B, and C. Well, we're going to add A and B together first, again by drawing a parallelogram, and we're going to get R. So now we're going to take R and add it to C, again drawing a parallelogram, and that gives us R prime. If we do that with example 7 down here, here we have A, B, and C. These are spread out at 120-degree angles, so they're going to points of a regular triangle, and they're equal in length. So if we do this, adding them up the first 2 and then add the next one, we add A and B, and we get R, and then we add R to C, and they are going in opposite directions, and they're equal in magnitude, and these things cancel out. When we have symmetry and equal lengths of the vectors, they're going to add up to 0. Any questions? So here's common cases of adding dipole moments. This has to do with the shapes that we see in the molecules from the Vesper theory. So linear. If you have 2 identical polar bonds, they're going in opposite directions, that's going to add up to 0. If you have a bent structure with polar bonds, you're going to get a net dipole because they're not in exactly opposite directions. So we can, see if we were adding this one, we'd have this line and, whoops, I missed. When we add those together, we have that red one that's going straight up. That's the situation with water. If we have a trigonal planar structure, we have these vectors, the dipole moments, are going in opposite directions. There's 3 instead of 2, but they're going in opposite directions. If they're all the same magnitude, then it's going to add up to 0. It'll be nonpolar. If we have a tetrahedral structure with equal dipoles, it's also going to add up to 0. This one's a little harder to see because now it's 3-dimensional space. And trigonal pyramid is going to be polar because you've got 3 dipoles, but they're all overall going downward, and so when you add them, you get a net dipole, and that'll be a polar molecule. Okay, now that we've covered all the how it really is, here's my shortcut. So a molecule is nonpolar if both of these conditions are true. There are no lone pairs on the central atom, and all the atoms bonded to the central atom are the same, or they have the same electronegativity. Usually what we'll see is they're either the same or they are different and do not have the same electronegativity. So any questions about that? Ms. Joyce? No? So let's apply this to predict Carlos. Okay, we'll just set it there. He wrote your name in it, that's why I thought it was yours. Let's use the shortcut and the more thorough method, and let's see if carbon tetrafluoride is polar or nonpolar. The first thing we have to do is draw Lewis structure. So carbon in the middle, fluorines around, and then we have to get the correct number of valence electrons and octets and all of that good stuff, and I'm not going to talk you through the details of that. There's our Lewis structure. Next thing is we have to decide what's the shape of this. It's tetrahedral. On the central atom, there are 4 groups. So the electron geometry is tetrahedral, and the molecular geometry is the same because there's no lone pairs. So this is the electron geometry and the molecular geometry. So this is a tetrahedron. Oops. And so what we have here is we have vectors of equal length, equal magnitude, because each of these bonds has the same electronegativity difference, right? Carbon and fluorine, carbon and fluorine, carbon and fluorine, carbon and fluorine. So we have a vector that's going up, and we have one that's coming out at this angle, and then there's one that's sticking out at us, and then there's one that's sticking back that way. In a tetrahedron, those 4 things are spread out equally in 3-dimensional space, and they're pulling in opposite directions. Can you kind of see how those vectors are going to add up to 0? It's hard. I'll give you that. So we can look at the vectors and say this is a nonpolar molecule. I find very few students who like to think about vectors. So let's do the other method, my shortcut. So start with the Lewis structure, and we have 2 conditions that we have to meet for it to be nonpolar. We have to have no lone pairs on the central atom. No lone pairs on central atom. Is that true? Yeah. Okay, check. Got that one. The second condition is that the atoms bonded to the central atom are the same. Are they all the same? Yeah, they are. Are the same. Okay, so that's also true. Check and check. Both conditions are met. This is nonpolar. And we did it without mentioning vectors. This works because if you have a lone pair on the central atom, that's going to make it unsymmetrical. It's going to make it polar, guaranteed, because it's going to be lopsided. So in order for it to be nonpolar, it has to be symmetrical. You can't have any lone pairs. The other thing about it being symmetrical, though, is that all of these vectors have to have the same magnitude. The difference in electronegativity between the central atom and the atoms bonded to it has to be the same. If they're all the same element, it's going to be the same. And that's the case most of the time. Usually, if you have two different elements, they are not going to have the same electronegativity. There are some, I think it was carbon and sulfur perhaps. I don't even remember which ones, but you can go look at the table of electronegativities and you can see that there are a couple of different nonmetals that have exactly the same electronegativity. So if those were on here, it would also be a nonpolar molecule. I will not try to trick you with that on an exam. Okay, any questions? So molecular shape, actually let's do one more example because I just don't think that was quite enough. Let's look at ammonia. So let's determine if ammonia is polar. Have to draw the Lewis structure first. Is that polar? Yeah, it is. You could do that really fast without thinking about what's the shape, how do the vectors add up. There's a lone pair on the central atom. That's going to make this lopsided. It's going to have a trigonal pyramid geometry. And so the vectors are all going towards the nitrogen. You add those vectors up, you're going to get a net dipole that's going straight up. But you don't have to think about all of this. You see the lone pair, bing, it's polar. So this one's polar. If we look at something like dichloromethane, polar or nonpolar? Polar. Why? The atoms are different, right? We've got hydrogens and chlorines. And so no matter how you make that tetrahedron, it's not going to be symmetrical. You can draw it symmetrically in the Lewis structure. If I put this chlorine down here and put the hydrogen over there, you can make it look symmetrical. But it isn't because it's three-dimensional. So this one is also polar. It doesn't have lone pairs on the central atom, but the atoms bonded to the central atom are not all of the same element. Okay. So, polar molecules and nonpolar molecules have very different properties. Oil and water do not mix together, do they? We experience this in the kitchen. You've got grease in your, oil from the meat in your soup or your gravy, and it rises to the top, right? You're trying to mix up the Italian salad dressing. It's got vinegar and oil, and the oil always comes to the top. The oil is nonpolar. The vinegar is water-based, and it's polar. The reason this happens is because of the polarity of the molecules. There's a negative end and a positive end in water. Opposite charges are attracted to each other like magnets. And so these water molecules act as little tiny magnets. It's electrical charge, not magnetic charge, but we understand magnets better. So they're attracted to each other, and they're going to stick together a little bit. Not a lot, but a little bit, and definitely more than a nonpolar molecule like an oil molecule that has no positive and negative end, and so there's no opposite charges to attract. So water molecules act like magnetic marbles. I've been trying to find some magnetic marbles. I went to a science museum in Oslo, and I was really hoping that maybe they had all these different magnet toys. No magnetic marbles. I need to get some. I haven't looked on Amazon yet. I don't know why. I don't go to the fair. The fair is overwhelming and a good place to lose children. Yeah, so and lose a lot of money because your children want everything. So yeah, I just don't go to the fair. But I could probably find them there. I could probably find them on Amazon too. And I just never think of it except when I'm giving this lecture. And I can't look on Amazon right now, can I? Actually, you guys wouldn't mind, but I'm not going to. Let's do it right now. Let's just take a break. Anyway, so you can imagine, though, here's regular glass marbles, and these are magnetic marbles. Magnets stick to each other, right? So if you put all these marbles together, what's going to happen? The magnetic marbles are going to clump together. If there are any glass marbles that get stuck between them, they're just going to kind of get pushed out, right? Because the magnets are going to stick to each other. That's what happens with polar molecules. They are very attracted to each other, and they push out the nonpolar molecules, and so they separate. The reason the oil is on top of the water is because it's less dense. There are other nonpolar liquids that will sink to the bottom of the water, and the water will be the top layer. But the fact that they separate into layers means that one's polar and one's nonpolar. It's also a little bit like cliques in high school. You know, there was that group of people, you know who they were, and they were just really tight with each other, and they had all these great parties and stuff, and here we are on the outside because we're science nerds, and we're like, oh man, they're just having so much fun. You can't get in there, right? You can't get into their group because they're too tight with each other. That's what polar molecules are like. Any questions? So how does soap work? You ever wonder about that? So, you know, you're making a cake or something and you grease the pan and you get Crisco all over your hands. Or you were eating buttered toast and you got butter on your fingers, right? Can you just rinse it off with water? No. Now, if you're sticky because you were eating candy, you can rinse that off with water, no problem. Sugar rinses off great. Butter, not so much. Why not? Because butter's nonpolar. Crisco is nonpolar. Water is polar. They don't mix together. So soap acts as sort of a go-between. This is an illustration of a soap molecule. So it's got this long nonpolar tail that's carbon and hydrogens. And they are so close in electronegativity that no matter what shape that is, it's nonpolar. So this nonpolar tail can mix in with the grease or the oil, whatever nonpolar thing you're trying to get rid of. This end of the soap molecule is polar, and so this will interact with the water. So what happens when you got soap and grease and water? So let's not do this in purple. Here's our grease molecule. Well, it's not a grease molecule, it's a blob, right? It's like when you make spaghetti sauce and then the orange from the tomato stuff gets in with the hamburger grease. You know, it's this bright orange stuff and you just can't get it off of anything. You need a lot of soap for that. I don't know what I'm talking about. So the nonpolar tail of the soap molecule will interact with that grease. And the polar head will stick out. And so it will surround these little globs of grease. This grease is not going to get washed off in the water because the water's like too tight with itself, right? It's like, I'm not letting you in, you're not cool. I don't know how to deal with you. When you've got this grease molecule, grease globule, with soap molecules in it, now what the water sees are these polar ends of the soap molecule. Those are magnetic. They have electric charge like the water molecules do, and so they can squeeze in with the water. This allows the grease, little bits of grease, to be made in small pieces and then be flushed away with the water. Any questions? It's kind of cool. I think so, anyway.